Okay, so we've been talking about something, I don't know. Governors, and now we're going to take this governor, we're going to attach it to a propeller. So let's talk about the operation. Operation of a prop. Hey, you know what prop we should use? How about a Hamilton standard? Does it sound familiar? All right. And this could be applied to some other ones. But what was the Hamilton standard we talked about? And a lot of times, or as we were looking at this picture, I said, well, it's a Hamilton standard. And I said, it's, did I go too far? Not far enough. Make you sick. All right. So Hamilton standard said it's a two position. Maybe. Maybe it's not. They also made this in a constant speed version. And so all you have to do is take out that valve and put in a governor, and suddenly it's more than just a two position prop. So let's look at how that works. So, all right. So we already know that the operation of a propeller, as we've talked about, we'll make it official now. For starting, takeoff, and landing, most props want to be in what position? Okay, so it should be the prop control is in the high RPM position. And which position is that? Is that pulled back or is that pushed forward? Okay, so that is forward. And what does that actually do?
That decreases the angle of the
It does, but how does it do it?
By releasing
more tension on the spring.
Pressure on the spring, which
Okay.
sends oil to the piston in the prop, in the hub of the prop.
Well, we can't go that far yet. This increases pressure on the speeder spring. Speeder. Which makes the governor think it's in what position?
Under speed.
Okay, so it tilts the flyweights in. Some little crude drawing here. There should be at 90 degrees. Okay, so it tilts them in, flyweights in. And I can't really say right now whether or not it sends oil to the prop or drains it, because I don't know what my prop's doing yet. Props work different ways, right, depending on how they work. But I can say with absolute certainty that it increases the pressure on the speeder spring, tilts the flyweights in, tells the governor that it's in an underspeed condition, and it needs to flatten those blades out so the engine spins faster, right? I hope I'm right. All right, so it does that, and it lowers the pilot valve. All right. Now, in this particular propeller, let's see. If I'm talking about the Hamilton standard, does it have flyweights? I'm sorry. No, it doesn't have flyweights. Does it have counterweights?
Yes.
It does have counterweights. So if it has counterweights, what do I need to do to make it flatten out? Does it want to flatten out? Does the Hamilton standard or a prop with counterweights want to go to low pitch by itself, or does it want to go to a high pitch by itself? Okay, so this thing, oh, my notes are actually incorrect here. So this, let me see. So it wants to go to a high, so it's going to add oil, right? Adds oil to the prop. And moves it towards low pitch.
So all Hamilton standards have weights?
I can't say all Hamilton standards because we're going to talk about the big version Hamilton standard. So talking about the counterweighted Hamilton standard. All right. Exception. What's an exception to this particular prop, this Hamilton standard?
The counterweights?
Well, okay, so I'm going to make a note. So Hamilton standard, or we can say at this point, any counterweighted prop. Because pretty much just about any counterweighted prop is going to operate this way. But the Hamilton standard is an exception. Exception. The Hamilton standard. Counterweighted prop should be shut down in the low RPM position. Do you remember why?
To hide the piston behind the cylinder.
There we go. Want to cover those parts up. But to start it, I can bring the lever up to the high pitch. So that's not a problem. I'm sorry. High RPM. High RPM.
Low pitch position?
Yep. The low RPM, back. Pull it back. Low RPM, high pitch. So that's the exception. All right, in cruise. So I'm cruising along, and this particular prop, and the pilot moves the control lever back to the, so pilot moves the RPM lever back to the desired RPM. So pilot moves the propeller control back to desired RPM. All right, so you're going to pull it back a little bit. And what's that going to do to the RPM?
Reduce the RPM.
Reduce the RPM, pull it back and reduce it. So at this position, the throttle mostly controls, mostly because you get to an extreme, it's going to change. Mostly controls what? Yep. MAP. What does MAP stand for? Manifold, absolute pressure. So when the control lever was pulled back, when the prop lever was pulled back, what happened?
Engage the governor.
It did. What happened in the governor? Okay, good. Speed or spring, we'll say tension, was reduced. So speed or spring tension was reduced, and so that means the flyweights are free to go into overspeed. And it was reduced, and flyweights went into overspeed. It went into overspeed. That means it's going to do what with the pilot valve? All right, so it's going to lift pilot valve and do what to the counterweighted propeller? What's that? Okay. So, okay, let's make sure that's right. Prop lever is pulled back, speed or spring tension reduced. Flyweights went into overspeed, so overspeed is where they're going to be out. Pilot valve is lifted up. And oil is, this is where we got to figure out oil is what? It's either sent to the prop or it's drained. And honestly, the way I like to kind of go about it is I start with, okay, I went into an overspeed, so what did the prop need to do? Need to increase pitch or decrease? Needed to increase pitch. Okay, we went into an overspeed, I got to increase pitch. What increased pitch on a counterweighted prop? Centrifugal twisting force. All right, so pilot valve is raised and oil is drained. From the prop. and centrifugal twisting force, CTF, because it has counterweights, moves prop to higher pitch, slowing the engine down to correct for the overspeed condition. And it's going to slow that engine down until those counterweights come into what position? On speed. All right, we'll get there in a minute. So let's see, overspeed. So pilot is flying along and just takes the yoke and pushes it forward. So some of the pilots I know, they've got the beer holder down here. And every now and then, I've actually seen this guy get out beer cans everywhere. Beer can comes out of the beer holder, and you got to reach forward to get it, and pushes forward on the yoke, right? Well, what's going to happen is a plane starts this nosedive. Right. Well, normally, the RPM wants to start increasing. So what's going to happen to the flyweights? Okay, going to go back into overspeed, which is going to raise the pilot valve and drain oil again. So, yep. And then, let's see. We just kind of covered that, really. And so it's all going to happen. The same thing's going to happen again. So it's just exactly what we talked about. Same as pulling the lever back. So overspeed. How can we make this a little quicker? If pilot pushes nose down, or to be realistic, let's say the pilot wants to actually start the beer thing is realistic, but pilot wants to start a slow descent. So puts in a little bit of nose down trim and just starts a nice descent. The engine's naturally going to want to speed up, or if the pilot decides to move the manifold pressure up a little bit, the engine would naturally want to speed up. So nose down or increases manifold pressure. How would the pilot increase manifold pressure? Yeah, we throttle forward. All right, so naturally the engine would want to speed up because it has more power, but it's not. So the governor has to correct. So the governor will overspeed. Will overspeed and right back what we just talked about and drain oil again. Increasing pitch. Now, if this prop did not have counterweights, then everything I'm saying would be the opposite. Everybody follow that? Okay. All right, overspeed. I think we can move on from there. All right, so on speed. Well, we'll give a textbook definition. When the flyweights and speeder spring are in equilibrium, the pilot valve, it doesn't allow oil to go to the prop, and it doesn't allow it to drain. So in a sense, what it's trying to do is lock the oil off that's in the prop. It's saying, whoa, you got the perfect pitch, let's just lock this down. And how well is that going to work? Okay, because we've tried to lock it down, but now we have the centrifugal twisting force. That doesn't go away. It's still out there trying to make the prop do something. Either go, if it has counterweights, go to a higher pitch. If it doesn't have counterweights, go to a lower pitch. So there's all this pressure. Plus, we'll talk next week, you may have a spring pressing on it. You may have air pressure pushing on it. There's stuff trying to happen in there. And so this oil is going to find a leak path. And where's the most likely leak path? Is it going to leak out the seals of the prop? No. I hope not, because that means it's leaving the prop blades. Is it going to, so what do we think? Have the prop, have the seals around all the moving parts. If it leaks there, it's going to go flinging out and lost forever. Next thing is there's a seal from the prop to the crankshaft. Should it be leaking there? I hope not, because the same thing, it's going to leak overboard, get on the windshield. Then we go through the prop again. Next thing we have is the transfer collar or the bearing. It'll leak there. Say yes. So yes, it'll leak right there. So we have a leak going on. So even if we could, according to the textbook, lock down the oil, it's going to leak out pretty fast. And then it's going to go into what kind of position? Well, I guess it depends on the prop. Could be underspeed or overspeed. So it's not going to stay locked very long. It's going to move. Well, it's going to move depending on if it's counterweighted or not. And oil's either going to have to add oil. Well, we'd have to add oil because the oil's leaking out. So speeder for the pilot. What was I saying here? Pilot valve. Neither allows oil to flow to or from the prop. That is an on-speed condition.
Does it say the pilot valve either allows oil?
Neither.
Neither allows. Okay.
So technically, if I had to be very technical about this, my own words now. So that's more of the textbook answer up there. But this is kind of not the textbook answer, so we just put an asterisk on there. So not really the textbook, but world according to me. And I will say during an on-speed condition, the governor supplies just enough oil pressure to balance the centrifugal twisting force and hold prop on speed. So during an on-speed condition, the governor supplies just enough oil pressure to balance out the centrifugal twisting force. I probably should just put a period there and hold the prop on speed. So maybe it's just adding a little oil. So in this kind of case, you can see it's not this all or nothing. It's not, oh, way over speed and way under speed and perfectly on speed. We can get it to a point where it's just kind of it'll move back and forth and add a little bit of oil, add a little bit of oil. Just kind of hold it right there. But in an absolute, perfectly equilibrium on-speed position where the pilot valve is being held perfectly square, then actually no oil can flow, and it doesn't. But I believe what's going to happen is it's going to constantly be going one way or another, just enough to lift it, add oil, add oil, add oil. All right, should we do underspeed? So underspeed, if pilot pulls back on the yoke,
That's why you get a pair on the back seat, right?
I was thinking that. I didn't know if I should say it. Yes. Like you knock the beer down underneath the rudder pedals. You can't reach it. Now it's spilled out. It's already fallen the floorboard. You got to reach in the back. Get another one. So you hold on the yoke and you reach back to get it. Or you're flying with my daughter, Mari. The first flight I had with my daughter, Mari, and you guys saw her, and it's been about a year or so, or even more. And so we take off. We're flying, and I said, would you like to try it? Yeah, I would, Dad. So I said, okay, take the yoke and you hold it. She takes it and pulls it right into her. That scared her a little bit, so she pushed it forward. So now we're doing this parabolic, and she's floating in the cockpit. She climbed up my arm and onto my head. And was all done with the airplane at that point in time. for, let's see, increases manifold pressure. Then the governor will go into an overspeed.
Oh.
Glad you're paying attention because I'm still thinking about my daughter flying. Underspeed.
You're thinking about that bait in the back.
Thinking about that beer in the back seat.
You'll have it back.
All right. I have a baggage compartment. And by the way, I did put Zeus in the baggage compartment, see if it would work. It was a bad idea.
You can get an overspeed and underspeed just by increasing the manifold pressure?
Yep, absolutely. But what will the RPM show? Yeah. So if I have an RPM gauge and I've got it set for, let's say, 2,500 RPM, in an overspeed condition, what will the RPM say?
2,500.
And when an underspeed, the RPM gauge will say, and on speed, it'll say, it doesn't move. That's the job of the governor, to keep it nailed right there. How can I move it off of 2,500? Move the lever. Which color? Blue. Okay, pulls. That will work. I will give you that. Going in underspeed. All right, so underspeed is flyweight's going in. Going to drop the pilot valve, and in this particular prop, it will add oil or drain oil. What's that? Add oil to prop to decrease pitch and increase RPM.
In my mind, I thought it had counterweights, then it drains the oil, so the counterweights will flatten out what the centrifugal is.
Nope. If you have no counterweights, the thing that flattens it is the blade itself.
Yeah.
Every time you add counterweights, you reverse the action. So I just went through a counterweighted type prop.
So Kevin, the speeder spring will do the same job there or no?
Just, yeah. It's got a set pressure. So the speeder spring doesn't move at all. But because when we slow down, right? Pull back on the yoke or increase manifold pressure. Hang on here. Did we just mess up? Pull back on the yoke. Yeah. Oh yeah. Pull back, or you're going to go into an underspeed. That's correct. Goes into an underspeed. So because there's not as much centrifugal force on the flyweights and you slowed it down, the spring wins. It pushes them in. Drops the valve. The valve is then going to send oil to the prop and flatten it out, and then engine speeds up and we go back into equilibrium.
So the difference between a counterweight prop and a regular,
Yes.
like the only difference will be the orientation of the flyweights.
No. Flyweights are the same all the time. I mean,
They're all the same orientation. So it's just the oil passages that are different.
Okay, so the difference between a governor that is made to go on a prop with counterweights and a governor that's made to go on without. Are they the same governor?
Yeah.
They're different.
All right.
But what is different about it is simply the pilot valve and how it goes inside. Yes,
Shouldn't it be decreasing manifold pressure?
that's what I meant to write. That's why I got screwed up there. Sorry. I knew something was... Thank you. Because I can't pull back on the yoke. That's right. It's going to slow it down. And then I just kind of... So decrease manifold pressure. Thank you for that. That's why that all was going weird on me. Okay, so the difference in governor is that... Let me write this down. Let's see. Say variations. Variations. In a governor for a counterweighted prop, underspeed I was wondering if I should do a chart in underspeed. What's that? We do a chart? All right, let's try that. Yeah, let's do that. That'd be fun. Okay. So what can we do here? Overspeed. Underspeed. Counterweighted prop. Non-counterweighted prop. So the governors look the same, but inside they're different. And what's different is the drive shaft and the pilot valve. I'm not sure which one if this will work for us, if this is going to be too much detail to pull up. Yeah. Let's not do that. All right. So in a counterweighted prop, which is what we've been talking about, and I'm thinking of better ways to do this, but we'll try it. Counterweighted prop. In an overspeed condition, the engine's going too fast, so we need to increase pitch, right? Increase pitch. So in a counterweighted prop, what increases pitch? Centrifugal twisting force to increase, and that means it drains oil. Drains oil. So centrifugal twisting force is our main thing, and it's going to drain oil. So we can just go the opposite then. So in an underspeed, what is going to correct the problem? Okay? Oil pressure. So oil pressure will drive it to underspeed, low pitch. Now if I have a non-counterweighted prop, and it's in an overspeed, which means it's too flat, what's going to drive it towards high pitch? Okay, oil pressure. And in an overspeed condition, underspeed, thank you, underspeed condition, which means we have too much pitch, what is going to relieve the pitch and bring it back towards?
Centrifugal twisting force.
Okay, centrifugal twisting force drains oil. So the job of the governor is to either add oil pressure or drain oil. Add oil pressure or drain oil. So that's all the governor's doing. You can have oil or you can't have oil. It's just say you get oil, no you don't get oil. Drain it off. Add some, drain it. Add some, drain it.
So on the non-counterweight, when it's in an underspeed, it's going to block off the incoming oil, so it'll route it back in.
Well, it actually has to drain it. It has to drain it from the prop.
No, I'm talking about the inlet from the pump. It's going to go through the relief valve and back
Yep.
to the inlet, and then
Yep.
from the prop it's going to drain.
Yes.
Okay.
So internally, yeah, don't forget that the pump's still turning. It's still a constant displacement. Oil's got to go somewhere. It goes around through the relief valve. So we could just put in a non-counterweight prop. Centrifugal twisting force is used to decrease pitch. Oil pressure is used to increase pitch. We're going to talk about feathering props more next week. And yeah, we'll talk about that next week. I'll add one more point here. And that point is, all right, so we talked about this leak problem that sometimes, what we do. We have a little bit of leakage between the bearings and the crankshaft, right? Or you call it the oil transfer collar in the crankshaft on the Continental engines. So you suppose there's some wear that can happen in there? All right, and so we've talked quite a bit about different things, so you should be able to troubleshoot some stuff. Pilot says, hey, my prop is really sluggish. What are some issues? Okay. Sluggish, that's spelled right? I think it's sluggish, yeah. So we could have what? Sludge in crank.
A one-out pump.
Let's stop there. Sludge and crank. What's the solution?
Take the prop off and clean the sludge out.
Yep. I had somebody, feeler gauges can get really long. I had a nice feeler gauge about that long that was sharpened into a knife. It's not a feeler gauge anymore. You get it right in there and just scrape it right out. And sludge is nasty. It's this grayish lead, and you can't get it off of you. It just stains everything. So sludge and cranks will desludge the crankshaft. Okay. What else I heard?
Oil pump.
Worn out governor. Specifically the oil pump. What's the solution for that?
Overhaul it.
Send it in for overhaul. All right. What's something else?
Where in the bearing or the collar?
Okay. Where between crank and transfer. Bearing or transfer collar. How am I going to, what am I going to do for that? Send what in?
You have to replace the collar or the transfer bearing.
All right, replace the collar or transfer bearing.
It's not really going to be your crankshaft.
So, how you suppose you change this part out? Well, you don't have to overhaul the engine. You just have to split the case. And then on a 6-cylinder Continental, when you split the case, you have to take apart the crankshaft and do non-destructive testing and have it ultrasound by a certified ultrasound shop. In order to do that, you pretty much got to take all this stuff off anyway, and then you got to change out the bearings. And if you take these apart, you have mandatory replacement items, all the the connecting rods and bolts and nuts. And then, of course, when you're there, you might as well change out the bearings. If you can do that, you might as well polish the crankshaft. So, well, if you've gotten that far, you might as well have the camshaft ground. And, well, shoot, what's the difference between that and an overhaul? Well, pretty much nothing. So, and then you do all that, and you take it apart, and you measure torque this together like that. You measure inside diameter. What would I use to measure the inside diameter of that? I will throw you out now.
You can put a T gauge in there. It's bad.
No, you can put a T gauge in there. It's this big around.
Oh, you mean when it's not on the...
What would be a better tool?
Got it.
Inside my phone.
Yes, that'd be a much better tool, in my opinion. You use what you want, because you guys are all pros and you can use it anyway. So inside micrometer would be my choice, but you can use what you like. You just know how I feel about those dang T gauges. So anyway, I take an inside micrometer and I measure this in a couple of different accesses. And by the way, I would not go this access because there's actually a little bit of chamfer right there. So that's always going to give you too much wear. So I usually go at about a access like that. So I measure that. I measure the crankshaft. I take the difference. I look it up in the book and it tells me the tolerance between the two. And I go, huh, look at that. It was good. I guess it must have been the pump. Should have had that overhauled first. So is there a way to figure out if that's good or bad before you get that far?
That's the pump.
You could send the pump out and have that overhauled. And that would be certainly a lot cheaper. But perhaps maybe owner says, man, I just had that done.
Probably that string in there.
Okay, I like that. I would probably say, well, maybe you had somebody put this together with a shoelace, and what's this gonna cause in pretty short order here? Well, if this is really what I think it is, which is not silk thread, it's going to add a space here that was never intended to be there. And so that space that was never intended to be there is going to have a space. Fretting is the correct word. So probably is going to fret, or the bearings will start to spin a little bit in there because they're not actually pinched like they're supposed to be. And then that string is going to wear away because it was never intended to be there. And then you're going to have a space, and the crankcase is going to start pounding like that. And then the studs are going to start flying off the cylinders. And eventually those cylinders are going to leave. And if it doesn't get to that point, this case is going to start leaking really, really bad. And at some point, somebody's going to put some sealant on the backbone of the case. That's going to look ugly. And then maybe eventually there's going to be a cylinder problem, and the mechanic's going to take the cylinder off. And then that mechanic's going to say, well, I learned how to put cylinders back on correctly. And they're going to take that cylinder and they're going to put it on correctly. And they're going to put the right oil on it. They're going to do a nice wet torque. And it's going to, all of this stuff in here that was fretted and now missing material, you're going to smash this together, and you're going to smash the bearings right on the crankshaft, doing the right thing. So that looks terrible too. Anyway, bad things are going to happen. But back to our dilemma at hand. There is a way to test this. I don't necessarily have a picture of that, but we can use this one. You have an inlet hole and an outlet hole. All you have to do is get a metal plate, aluminum plate that fits over this. And they're easy to find because not all aircraft use this pad, and so they actually make plates that go here for those people who aren't using them. So you take that plate and you can modify it, so with a fitting here and a fitting over here. So actually just a fitting up here would be fine. One fitting, and you can hook it up to a differential cylinder compression test. And you can put a certain amount of air into this hole. And if you have a really tight bearing and transfer collar, guess what? You're not going to have a lot of leakage. And so there's a Lycoming service instruction that tells you exactly how much pressure to put in and exactly how much pressure is good and how much is bad, and if you have a excessive wear between those parts. So differential cylinder compression test will tell you the answer. Questions?